All righty, gang, welcome back. Today, there we go, sorry about that. Welcome back. Today, we're going to finish talking about power series, basically. We're going to look at a handful of new examples using power series to solve problems that previously were inaccessible to us. And I'll show you how to use the series that we've come up with already in order to develop more and more series kind of as needed. So the goal for today is to try and develop a level of comfort with the tools and objects we've been introducing lately. Really quickly, I'm excited to share this with you because this is something I'm doing with my honors calc class. There are other ways besides power series to approximate functions. So if you take this function right here, which is a fairly simple guy, he's 0 until you get to 0, and then he's 1 thereafter. He's piecewise constant. Might seem like a silly thing to try and find an approximating series for. I'd like to point out that you could not find a power series for this. There is no power series for this function because remember, power series are infinitely differentiable. The requirement is that f have derivatives of all order in order to find a power series for that function. This function has a jump discontinuity here at 0. So there is no way to find a power series for this function. However, there are these things called Fourier series, which are a little bit more powerful than power series in the sense that you can find a Fourier series for functions even if they're really badly discontinuous. And the picture here, I think, is just really neat. Watching this Fourier series converge to the square wave function we have there. So I'll set this to run just forwards. Kind of like watching a power series converge, only very, very different in the sort of behavior. I think it's pretty nifty. What we're really doing here is writing our function as a sum of sines and cosines. So I just thought it would be a neat thing to share with you. I had fun making this. Anyway, you've probably noticed that pretty much all the exams are graded. I think there are like 3 or 4 that I wasn't able to finish yesterday evening. I'll be wrapping those up today. There were some issues here. I don't want to spend a lot of class time talking about it, but there were a few tests where there was some pretty obvious cheating, like shit copied verbatim from Mathway. Mistakes, kind of strange mistakes that showed up identically on more than one test. Things that are obviously not math mistakes, but copying mistakes. So those sort of things, that stuff is not okay. Take a look at the feedback I left on the tests, and if I asked you to contact me, please do so, because if you and I can talk rather than it just being managed through the conduct office people, then I have the ability to kind of push for some leniency. So everybody makes judgment call mistakes from time to time. And if that's something that happened here, then the best move for you is definitely to kind of come clean with me and talk with me about it. That way I can talk to Rodkin's office and recommend leniency and recommend that it be handled gently. But you've heard me talk ad nauseum about the importance of academic integrity, especially in exams, especially in math classes. So I won't continue with that. I'll just say, please look at the feedback I left on your exams. And if I ask you to contact me, please do so. It is in your best interest to do that. So with that said, this is MAC2312, section number 004, which is Calc 2. The date today is the 30th of March, 2022. And the name of the game today, we're going to be talking more about Taylor and Maclaurin series. I think we said this the other day, but a Maclaurin series is just a special name for a Taylor series that's centered at 0. I want to begin the day by kind of recapping the major developments that we have. oh, major, not result is just major results. We learned that if you have a function that can be written in the form 1 over 1 minus u, that can always be expanded as a power series, sigma n from 0 to infinity of u to the n. And the IOC here is the open interval from -1 to 1. From this, we were able to get a whole bunch of things. One was a power series for the inverse tangent function, which I'll write as inverse tangent of u. I'm using the symbol u here for a reason, and that should become clear in just a moment. This guy can be expanded as a power series, sigma n from 0 to infinity, -1 to the n over 2n plus 1 times u to the 2n plus 1. And his IOC is the closed interval from -1 to 1. We're also able to get a series for the natural log function in the form natural log of 1 plus u. And this guy is sort of an alternating harmonic-y thing. The version of this series that appears in your textbook starts at 1 rather than at 0 and has a slightly different form. I think it's easier to remember in the form I'm going to write it here, but either one you like. This is how I remember it. Sigma n from 0 to infinity, -1 to the n, divided by n plus 1 times u to the n plus 1. And her IOC is left open, right closed, -1 to 1. So these were the major results that we were able to cook up back in section 11.9. And then just recently, we got power series for the exponential function. E to the u. The IOC here is all real numbers. We're able to get power series for sine. Sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times u to the 2n plus 1. And the IOC for the sine series was also, let's see, here was also -infinity to infinity. And the last one was cosine. Which is very similar to the sine series, just with 2 n's instead of 2n plus 1's. And the IOC here, again, -infinity to positive infinity. So these are the power series that you need to remember forever and ever. Right? These are the power series that we will use quite regularly. And these should be the starting point for most of the problems, not the end point. This is where you begin, and then you can use these to get more complicated power series or to solve problems, stuff like that. In other words, you got to commit these to memory. The other kind of major result was Taylor's theorem, which was that in general, you can write an arbitrary function, f of x, as long as it is infinitely differentiable at a, as the sum from n equals 0 to infinity, and derivative of x evaluated at a over n factorial times x minus a to the n. And this was the recipe that we used to get the bottom 3 power series up there. We've written this as Cn times x minus a to the n, and then said where Cn is this thing. This is the way you write it sort of all at once. I cannot say what the interval of convergence is in general for something like this because it depends very much on the function f and what these numbers come out to be. But this is a recipe that we can use to come up with power series if we cannot get the power series we want from any of the guys above. One classic problem, so the idea is that having access to these other ways of writing functions allows us to do stuff that is sometimes very hard. For example, we saw at the beginning of the semester, some integrals are incredibly hard. Some integrals are straight up impossible, right? Like there is no closed form antiderivative for a lot of functions. If you can write that function as a power series, however, then you can go ahead and integrate the function by integrating the series. Also, certain limits are much easier to do in terms of series than using, say, L'Hopital's rule or something. So today I want to show you lots of examples of that stuff. Let's do it. A classic problem. It was discovered pretty early on in statistics that if you look at what's called a Bernoulli random variable, that is a thing you can measure that is sort of distributed according to certain rules, like height. If you look one gender at a time, right? Because men on average are a little taller than women still. If you look one gender at a time, height is normally distributed according to a limit of a Bernoulli random variable. The probability distribution function for most things like that is something like this. It's e to the negative x squared. And if you want to know, for example, how many people or what percentage of people have a height less than a certain amount or greater than a certain amount, you would have to integrate some slightly modified form of this, shifted and maybe stretched or compressed a little bit. So integrals of this form, very, very important in statistics, probability, physics, other places like that. The challenge is that try as you might, you'll never find a nice looking function whose derivative is e to the negative x squared. Right? You could take the derivative of this, but you cannot find an antiderivative for this in terms of so-called elementary functions. So much so that this guy, the antiderivative of e to the negative x squared, which does exist, you just can't write it down nicely, is given a formal name in higher mathematics called the error function. So what we're going to do here is we're going to find an expression for this guy. It's not going to be a so-called nice expression. It's not going to be a finite combination of elementary functions. It's going to be a power series. So the first step is to write the function inside here as a power series. The trick to this and all problems like it is not like I expect you to know a power series for this off the top of your head. You start with a power series that we do know, and then you can plug in or modify that series as necessary to get a series for this guy. So I'll begin by saying we know, and that's why I wrote those all in terms of u, because then you can kind of think of it as plugging in for u. We know that e to the u is the sum from 0 to infinity 1 over n factorial times u to the n. So e to the negative x squared, we're going to plug negative x squared in for u. That should be sigma n from 0 to infinity 1 over n factorial times negative x squared to the n. My end goal is to integrate this thing, so I want to integrate this thing. But before I do that, I really want to simplify this. My formula for the integral of a power series assumes that you just have like x to the n, or x minus a to the n, not negative x squared to the n. So you must simplify this before doing the integral. The 1 over n factorial is going to stay, and I'll just write the n factorial downstairs. Negative x squared to the n is this negative 1 to the n times x squared to the n. Negative 1 to the n, we'll put up here. And x squared to the n is x to the 2n. It's the same sort of thing we did when we found the power series for arctan of x squared. Just going to put a little note here that you must simplify this before integrating. So I need my simplified series, then I can take the integral. Any questions about how we get this power series for e to the negative x squared? So we can say, therefore, the integral of e to the negative x squared dx is going to be the integral of this power series. Like so. And recall that to integrate a power series, you basically cover all this stuff up. You just pretend like you're integrating x to the 2n. Everything else comes along for the ride. Because we're doing an indefinite integral, we do get a plus c here. The sigma n from 0 to infinity, negative 1 to the n over n factorial stays. When you integrate x to the 2n, you get x to the 2n plus 1 divided by 2n plus 1. And so multiplying. I'm of the opinion that it's nice to rewrite this with all the coefficient stuff together and the x stuff separate. So before I walked away from this problem, I would combine the negative 1 to the n over n factorial with the 2n plus 1, giving me this. And then something you'll be asked to do somewhat often is to give the first like 4 or 5 terms, something like that. So I could ask you, for the first 4 terms, 4 non-zero terms of the answer, you just have to start writing out the terms of that power series then. So if we wanted this in the expanded form, we just need to take this series and write out the first few terms. When n is 0, we get negative 1 to the 0 over 0 factorial. Those are both 1 times 2 times 0 plus 1. That's also 1 times x to the 2 times 0 plus 1. So the first term of that series is x. When n is equal to 1, you get negative 1 to the 1 divided by 1 factorial times 3. That's minus 1/3. And then x to the 3, x to the 2 times 1 plus 1. When n is equal to 2, you get negative 1 squared is positive 1 divided by 2 factorial times 5. This is plus 1 over 2 factorial times 5. Now 2 factorial is 2, so you could write this as 10 if you wanted, times x to the 5. And the next term would be minus 1 over 3 factorial times 7 times x to the 7, and it goes on like that. Any questions on what we did here? Just a quick reminder of some notation. The Taylor polynomial T1 of x would be c plus x. The Taylor polynomial T3 of x would be c plus x minus 1/3 x cubed. The Taylor polynomial T5 of x would be c plus x minus 1/3 x cubed plus 1/10 x to the 5. So if you're asked for any particular Taylor polynomial, you just take the series expansion up to that order term. So T5 stops at x to the 5. So this is T5. T3 stops at x to the 3. So this is T3. T1 stops at x to the 1. So this is T1. Here, T2, I haven't written because T2 would be the same as T1. There is no x squared. So if you stop at the x squared, that's the same as stopping at x. T4 would be the same as T3 because there is no x to the 4. So it'll just be this. And a fun game to play is to graph some of these Taylor polynomials, the partial sums for this series, together with the actual function. And Desmos is pretty good at this. You just have to kind of bullshit it a little bit because of the plus c. So to get around the whole constant thing, I'll integrate from 0 up to x e to the negative t squared b. Say y equals, here he is. And then t1 of x, I'm going to plug in 0 for c. Would just be x. T2 of x would be x minus 1/3 x cubed. Oh, sorry, not T2, it's T3. T5 is x minus 1/3 x cubed plus 1/10 x to the 5. And what you see is that the Taylor polynomials are doing a pretty good job of, Desmos having a hard time with this. These Taylor polynomials do a good job of approximating the red function, as long as you stay close to the center, right? The black and the red here, very, very close to each other, as long as you stay close to the center. If you use enough terms, because the interval of convergence for this series is all real numbers, right? We started with the series for e to the u, which has IOC, all real numbers, and none of the stuff we did here is going to actually change that. So if you were to give yourself a lot of terms, like we can throw T7 in here. And then T7 would be 1/3 factorial 6 times 7 is 42. So minus 1/42 x to the 7. It's blue or something. You see that the blue does a slightly better job of sticking to the red than the black does. Just sticks tighter a little further. And the more and more terms you use here, the better and better these will stick to the red. That's the game. And this whole universe of stuff is open to us now that before would have been completely impossible. Questions at all about the Taylor polynomial notation or how we're getting these from this? Oh. This is an x, or 5 hidden change, so badly drawn 3. That's an x cube. Okay. Another fun thing we can do, like I said, is we can take limits. I have a few simple ones in mind, but I want to look at one that's a little bit challenging because you do have a couple of these in your homework. Let me see what we can do here. Find a fun. This is good. E to the x minus 1 minus x over x squared. There are other ways to calculate this limit. First, observe that if you just try to plug in 0 for x, this would be e to the 0, which is 1. 1 minus 1 is 0. 0 minus 0 is 0, so the top is 0. And of course, if you plug in 0 down here, 0 squared is 0. So if you just plug in 0, you get 0 over 0, which means you could attack this with L'Hopital's rule. But we were told to do it by a power series, and there is something to this approach. The power series approach gives you better insight. So again, the trick is to begin with the fact that e to the x can be written as a nice power series, sigma n from 0 to infinity, 1 over n factorial times x to the n. You could just plug this sigma expression in for e to the x here, but that's going to make this thing look real damn scary. So for all these limit problems, my advice is to, instead of plugging in the sigma form of the power series, write it out, long form in the dot, dot, dot notation, and plug that in. So when n is 0, we get 1 over 0 factorial x to the 0. When n is 1, we get 1 over 1 factorial x to the 1. When n is 2, we get 1 over 2 factorial x to the 2. When n is 3, we get 1 over 3 factorial x to the 3. And so I'll just stop at the x to the 4. But we know it continues on like this forever. I'll simplify this a tiny bit, and then we're going to plug it in. 0 factorial is 1. So this is 1 over 1 times x to the 0. X to the 0 is also 1. So this first term is just 1. 1 factorial is 1. So this is 1 over 1 times x to the 1, which is just x. 2 factorial is 2 times 1, which is 2. So this is 1/2 x squared. 3 factorial is 3 times 2 times 1 is 6. So this is 1/6 x cubed. 4 factorial is 4 times 3 times 2 times 1 is 24. So this is 1 over 24. So this is what I'm going to plug in for e to the x here. And we want to make sure to write the whole fraction with our limit up front when we do this. So we can say, therefore, the limit as x goes to 0 of e to the x minus 1 minus x over x squared is equal to limit as x goes to 0 of, I'm going to put in parentheses here for this e to the x, this expression. 1 plus x plus 1 squared plus 1 cubed plus 1 4 plus dot 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 minus 1 x. Squared. So I just take this expression, and in place of e to the x, I write the power series for e to the x. And spiritually and morally, it's the same thing as what we did with the integral. Right? Replace the function by its power series to make the calculus operation we're trying to do easier to work with. The power series might seem a little intimidating. The truth is we can handle them the same way we handle polynomials, which makes life very nice. Polynomials are very nice. Now I have a +1 here, and a -1 here. I have a plus x here and a minus x here. Those will eat each other up. And I'm left with when x to 0, the 1 plus x are gone, so I just have 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4 and so on, divided by x squared. So if I divide each of those terms by x squared, you can think of it like I'm going to bring this upstairs as multiplied by 1/x squared. That's the idea. And then distributing that, you get 1/2 plus 1/6 x plus 1/24 x squared. Oh, and all of the terms here have an x in them. So as x goes to 0, this is going to go to 0. This is going to go to 0. The next term there is 1/120 times x cubed. Well, that's also going to go to 0. So we get 1/2 plus 1/6 times 0 plus 1/24 times 0 squared, and so on. Just 1/2. These are not too bad, but you do need to practice them a little bit. They are very likely to show up on the exam. So I want to encourage you to take the time, practice the applications. The best way to test power series, Taylor series stuff isn't to just say, find me a power series for this. It's to say, go ahead and do something, right? Do something that requires finding a power series first. And there will be problems of both types. So any questions on what we've done here? And just for the record, this would take 2 runs of L'Hopital's rule if you wanted to do it that way. But it's very easy to kind of extend this problem in a way that would require 10 or 50 runs of L'Hopital's rule. The power series solution would take the same amount of time, but the L'Hopital could take longer and longer and longer depending on how I modify the problem. So it might not seem like it's superior to L'Hopital's rule here, but it is because it generalizes much better. These are the 2 main kind of application problems you're going to run into. We can take a look at maybe one more integral, and then I want to walk you through another straight up Taylor series problem or Taylor's theorem problem. This time, let's try a definite integral. I'll just say as a series. The result here is not going to be a power series, it's going to be a number because we're doing a definite integral, but we will use power series. I think I've mentioned before this function sin x over x is quite famous. It's called the sinc function, very important in signal processing. Integrating it from, oh, we can't go from 0. Actually, we can. Yeah, that's okay. It might appear to be an improper integral because of the 0 here and the x down here. But remember, sin x over x, the limit as x goes to 0 there is 1. So it's actually not improper. I'll make a little note about that. The limit as x goes to 0 of sin x over x. We might think that this function has a vertical asymptote at 0, but this limit is 1. This was the limit that we worked with back in Calc 1 when we were discovering the derivative of the sine function. You can get it with L'Hopital's rule if you want. So where do we begin? We begin with the power series for sine x, which is sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And what I want is a power series for sine x over x. The trick there is to say, okay, well, I know what sine x is, and I know that dividing by x is the same as multiplying by 1 over x. So then if I plug in my series for sine, when I push this x inside, I have 1 over x times x to the 2n plus 1. Well, this is x to the -1 times x to the 2n plus 1. So that gives me the sum from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n. Therefore, the integral from 0 to pi of sine x over x dx is the same as the integral from 0 to pi of that series. I love just writing things like this on boards at the library or in a classroom and leaving them up there to scare the living shit out of college algebra students. It's always fun. The game, like the very first problem we looked at, is to just kind of pretend like this isn't here. What we're really doing is integrating from 0 to pi x to the 2n. All right, in other words, we're integrating the series one term at a time. Because this is a definite integral, not an indefinite integral, there will not be a plus c here. We're we're going to take our result. This stuff stays the same. Integrate x to the 2n, you get x to the 2n plus 1 over 2n plus 1. And we're going to evaluate this from x equals 0 up to x equals pi. When you plug in 0 for x here, every term of the series is 0. Because this guy is 0. So you get a bunch of stuff times 0. So the result -1 to the n over, I'll combine these things here. So this is 2n plus 1 factorial times 2n plus 1. And then upstairs, you're going to have a pi raised to the 2n plus 1. Pretty neat, right? And again, this is a number. If you want to approximate that number, you look at a partial sum for this series. So I could ask you to use the estimation theorem for alternating series to approximate this to some level of accuracy, like 2 decimal places, or with an error smaller than 0.001 or something like that. It would come from a partial sum at n equals 0. This is 1 over 1 factorial times 1 with pi to the 1 upstairs. So that's just pi. When n is 1, you'll have negative 3 factorial times 3 times pi cubed, or pi cubed over 3 factorial times 3. When n is 2, you'd have positive 1 over 5 factorial times 5, and then pi to the 5 upstairs. And it'd continue like this, minus pi to the 7 over 7 factorial 7 plus pi to the 9, blah, blah, blah. One of the things I saw on the exam grading is that a lot of us struggled a little bit with using the estimation theorem. So let's go ahead and do that. Let's give ourselves a set precision and say, now approximate the integral from 0 to pi of sine x over x dx with error, and say less than 0.001. The series I'm working with here is an alternating series, so I can use the alternating series estimation theorem. Which says that the absolute value of s minus sn is guaranteed to be less than bn plus 1. And if I want, so this thing is the error. If I want to make the error smaller than 0.01, I know the error is smaller than bn plus 1, so it suffices to solve the inequality bn plus 1 is less than this desired error, 0.001. The bn's in this series are everything except the -1 to the n. Off to the side here, I'll say bn is pi to the 2n plus 1 over 2n plus 1 factorial times 2n plus 1. So b sub capital N plus 1 is what you get by taking all of these little n's and replacing them by capital N plus 1. That's pi to the 2 times cap n plus 1 is 2n plus 3 divided by 2n plus 3 factorial times 2n plus 3. And I need this to be less than 0.001, which is 1 over 1,000. We can rearrange this just a little bit, but from there we're going to work more or less guessing. Because there's no nice way to solve an inequality like this. The factorials make life really hard. So this is the same thing as saying 2n plus 3 factorial times 2n plus 3 divided by pi to the 2n plus 3 is greater than 1,000. So we can plug some numbers in here and see where this happens. When n is 2, we have 4 plus 3 is 7 factorial times 7 divided by pi to the 7. And we can compute that. This is like 11.68. That's definitely not big enough. When we plug in n equals 3, this will be 2 times 3 is 6 plus 3 is 9. So 9 factorial times 9 divided by pi to the 9. Should be getting bigger, 109.56. But still not bigger than 1,000. I'll stay in Desmos here, but when n is 4, we're going to have 11 factorial times 11 over pi to the 11. Which is 1,492.45. So the first time this inequality is true is when n is equal to 4. First integer where that is true. So S4 will give the desired accuracy. And S4, remember what our series was. Our series was this guy. So S4 would be the sum out to n equals capital 4. Negative 1 to the little n, pi to the 2n plus 1 divided by 2n plus 1 factorial times 2n plus 1. Which is just like this is 0, 1, 2, 3. So we need one more term. That next term is pi to the 9 factorial times 9. So this finite sum will have an error less than 0.01. Yeah, I can go back in just a second. Here we go. So there's all the approximation work. Questions on any of the steps here? In doing this, we've actually gone beyond the capabilities of Desmos, but I can check and verify our results here using the more powerful computer algebra system Wolfram. I'm going to do that in just a moment, so if you need a screenshot or something, now's a good time. So if I want to integrate, so let's go for that. And it'll do its best job. On the other hand, we could sum 1 to the n over 2 plus 1 times 2 plus 1. Oh, now we need a pi to the 2 plus 1. Oh, it doesn't like the sum. Oh, and it also, I see, I left off of. There we go. All right. So what we see is that our little partial sum here, just these 5 terms, gives me 1.8525. Roll it down. 1.8525. We'll do one more, 7. And by Wolfram, the actual value of the integral was 1.85194. That's, I guarantee you that's an approximation also. So the thing we found compared to the actual value, 1.852, 1.851, you see we're off by only 1 digit in the thousands place. And because this is a 9 and this is a 5, we're actually off by less than 0.001. But that's the idea. Most of those fancy tools like Wolfram, in fact, the way they compute this is precisely what we did here, only they default to using more terms. That's the game. These are incredibly powerful mathematical tools, right? These are the mathematical tools that the modern world is built around. This is how we solve the differential equations that got us to the moon. This is how we solve the mathematics problems behind signal processing, circuits. All of the cool stuff that makes the modern world modern relies very heavily on this specific bit of mathematics. So if you intend to be someone who contributes to or helps those things develop in your career, some kind of engineer or scientist, then these methods are going to be hugely important for you. Questions on calculating the integral or using the estimation theorem to get a desired level of accuracy? I have one other kind of fun problem for us. Kind of two other things I was hoping to do today. One of them was to show you a silly problem involving derivatives. The other is, I guess, a little more serious. We need to practice calculating one other kind of power series here. So let me go ahead and do the power series calculation first. And then if there's time, I'll do the sort of silly fun derivative problem. So let's find a power series for this function. F of x equals the square root of 1 plus x centered at a equals 0. This is actually a special case of something called Newton's binomial theorem, which is the power series from 1110 that I told you don't need to memorize. The reason I told you don't need to memorize that is because it involves these things called binomial coefficients, which are perfectly fine if your power or the numbers inside the binomial coefficients are whole numbers. But if they're not whole numbers, like here the power is 1/2, those binomial coefficients become hard to interpret. So my advice for you at this level, rather than trying to memorize that very strange formula, is to go through a few calculations, right? Practice, and then if you want to memorize that formula, you can. But if you have any hope of understanding what like 1/2 choose 3 is, you're going to need to see how this unfolds. So let's do it. This is definitely not like e to something or sine of something or arctan of something. It's none of that shit, right? So I cannot get this by plugging into any of my known power series formulas, which means the only way I can attack this is through the Taylor theorem, meaning it's time to build the table. The columns for this table, as always, are n, the nth derivative of f, the nth derivative evaluated at my center. So again, here my center is 0, and then Cn, the nth Taylor coefficient. I'm going to give myself lots and lots of space here because the derivatives for this function will get a little nasty. But we can handle it. When n is equal to 0, I'm differentiating my function 0 times. I'll write this as 1 plus x to the 1/2. That's the 0th derivative. If I plug 0 in there, then I just get 1 to the 1/2, which is 1. So C0 is 1 over 0 factorial. Good start. If I differentiate this function once by the power rule and the chain rule, I get 1/2 times 1 plus x to the negative 1/2 times the derivative of 1 plus x, which is 1. Evaluating this at 0, I get 1/2 times 1 to the negative 1/2. And that's 1/2. Dividing this by 1 factorial, I get 1 over 2 times 1 factorial. Differentiate again. The derivative of the object above there is 1/2 times negative 1/2 times 1 plus x to the negative 3/2. Let's see that negative. Evaluating this at x equals 0 gives 1/2 times negative 1/2 times 1 to the negative 3/2. I don't have room here to write it. This piece is just 1. So we're going to have 1/2 times negative 1/2. So that's negative 1 divided by 2 times 2 is 2 squared. And then we divide through by n factorial. So there's going to be a 2 factorial here. Unfortunately, the pattern gets a little more complicated after this. Some more space because we're going to need it. If I differentiate again, I'll have 1/2 times negative 1/2, bring the power down times negative 3/2. Times 1 plus x to the negative 5/2. And when you evaluate all of this at x equals 0, this piece becomes 1, and you get 1/2 times negative 1/2 times negative 3/2. All right, though, 1 to the negative 5/2, so I still have space there, but we will run out of that soon. So what do I have all together? I've got 2 times 2 times 2 downstairs. That's 2 cubed. And I know Cn I divide by n factorial, so there's a 3 factorial downstairs. Upstairs, I have 1 times negative 1 times negative 3. I'm going to write that as 1 times 3. We're going to do like 2 more rows of this. If I come back and differentiate this again, these constants just stay. So this is 1/2, negative 1/2, negative 3/2. The derivative of 1 plus x to the negative 5/2 is negative 5/2. 1 plus x to the negative 7/2. Plugging in 0 for x, this piece just becomes 1. So I just have these numbers. 1/2, negative 1/2, 3/2, 5/2, and then I'll have the 1 to 7/2. Simplifying this a little bit and dividing by 4 factorial, I get downstairs 2 times 2 times 2 times 2. 2 to the 4. I divide through by n factorial, so there's a 4 factorial. And then upstairs I have 1 times negative 1 times negative 3 times negative 5, which I'll write as negative 1 times 3 times 5. What we see is a kind of strange product forming upstairs. It's one of these, you saw them when we talked about the ratio test. It's not a factorial. It's kind of like a factorial, but it's missing terms. It's just got the odd stuff in there. I'll do one more, and then we're going to go hunting for the pattern. If I differentiate this again, I get 1/2, negative 1/2, negative 3/2, negative 5/2, negative 7/2 times 1 plus x to the negative 9/2. When you plug in 0 for x, this whole piece becomes 1. You just get this crazy product out front. 1/2, negative 1/2, negative 3/2, negative 5/2, 7/2. And this is going to be a 1 to the negative 9/2, which is just 1. So yeah, this piece is 1. I just need to look at these and then divide by 5 factorial. Downstairs, I have 2 times 2 times 2 times 2 times 2, which is 2 to the 5. Let's start there. And then the 5 factorial from the formula. Upstairs, I have 1 times -1 times -3 times -5 times -7. So that's 1, 2, 3, 4 negatives. So it's going to be positive. 1 times 3 times 5 times 7. We're going to stop here and ask for patterns here. What do you see in these things? I know it's a little tough. When n is 1, I have a 2 to the 1. When n is 2, I have a 2 to the 2. When n is 3, I have a 2 to the 3. When n is 4, I have 2 to the 4. When n is 5, I have 2 to the 5. I am confident that the denominator has 2 to the n. Similarly, I've got 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. My denominator is definitely 2 to the n times n factorial. Positive, negative, positive, negative, positive, negative. This is an alternating thing. When n is 1, we're positive. When n is 2, we're negative. When n is 3, we're positive. So that means there's a power of -1 here. And when n is odd, we're positive. When n is even, we're negative. So it's not n plus, it's not -1 to the n, it's -1 to the n plus 1. You could also write n minus 1, doesn't matter. And then the hard part. The hard part is like, what about the 1, 3, 5, 7 stuff? How do you write that? If you think back to a few of those ratio test problems, you've seen products like this before. You write 1 times 3 times 5 dot dot dot, and then you tell them where this product ends for the nth guy. So yeah, the catch here is that it's not a factorial, right? This is not 7 factorial. It's a reasonable thought, and I think this is what makes this hard. Because 7 factorial, that would be 1 times 2 times 3 times 4 times 5 times 6 times 7. So the numerator, that product up there, is actually missing half the terms of the factorial. There's a name for this thing, it's called a double factorial, but multifactorials are definitely beyond the scope of this class. I don't want to spend time introducing and showing you that notation. The way the textbook writes this is fine. You just have to describe the pattern in the product. So it's like 1 times 3 times 5. When n is 5, this ends at 7. When n is 4, this ends at 5. When n is 3, the product ends at 3. Definitely these are odd numbers. We could try 2n minus 1, but 2 times 5 minus 1 is 9. This doesn't end at 9. It ends at the odd number before 9. So that's 2 times 5 minus 3. So this product will end at 2n minus 3. And that is your formula for the nth Taylor coefficient, with one tiny caveat. This formula makes sense if n is bigger than 2. You cannot plug n equals 0 into this product. So this is correct. But only for n greater than or equal to 3. Sorry, n greater than or equal to 2. Yeah. 2 times 2 minus 3 doesn't make sense. All right, if you plug in 0 here, this would say multiply every other number up to -3. Oh, that doesn't try to make sense. If you were to try and plug n equals 1 in here, also doesn't make sense. 1 times 3 times 5 all the way up to -1? No. But for n 2 or greater, this says 1 times 3 times 5 all the way up to 2 times 2 minus 3, which would be 1. So this works fine when n is 2. When n is 3, this says multiply 1 times 3 times 5 in that pattern all the way up to 2 times 3 minus 3, which is 6 minus 3 is 3. So that would just be the 1 times 3. Yeah, sure. Yeah. So how are we going to take this and write down our power series if my formula for the Cn is only valid when n is greater than or equal to 2? Well, Taylor's theorem says this. And I can use my formula. I can plug this formula in here for Cn, but not when n is 0 and not when n is 1. So we just pull those terms out. That's C0 plus C1x plus the remaining terms are the sum from n equals 2 to infinity. Now within this sum, n is bigger than or equal to 2, so I can use this formula. C0 and C1, I actually calculated those as a part of this exercise. Ooh, what the hell? What have we done here? Hit something. Shit. How do I close those? Just 1 second, something weird happened with the dot cam here. No, I didn't hit anything there. What did I hit? Text clear. And all drawing tools. What the fuck did I hit? Let's try just bringing this back. No. Okay. No, that did not work either. I guess. Our first thing here. Yeah. Ooh, what did something? My camera. There. Oh, no. These are old saved things. There we go. Okay. Oh my God, are you kidding me? Okay. All right, almost there. So this formula for the CNs, which we found, is good and correct as long as n is bigger than or equal to 2. So we take our power series, and we just need to pull out the n equals 0 and n equals 1 term. This is the n equals 0 term. This is the n equals 1 term. And what's left is the sum from 2 to infinity. So in this expression, I can plug in my Cn formula, and C0 and C1 I've already calculated. They're 1 over 0 factorial, which is 1, and 1 over 2 times 1 factorial, which is 1/2. So what we get here is, I'll write the answer down here, square root of 1 plus x equals C0, which is 1, plus C1x, which is 1/2 x plus the sum from n equals 0 to infinity, -1 to the n plus 1, 1 times 3 times 5, terminating at 2n minus 3, divided by 2 to the n times n factorial, all times x to the n. That is the power series for this function. This is as challenging as these problems will get for us. Out there in the real world, they can get harder still. But this is about as hard as anything I could ever ask you to do on a test. And even then, I probably wouldn't ask you for this full formula. I might ask you for like the first 5 terms of the series or something. So you could get there just by calculating these coefficients and then writing out the terms. But it is a skill you want to work on developing. I think I gave you only one homework problem that is sort of this level difficult. There are many more if you want to practice them in the textbook, but I don't feel comfortable. I don't feel like it's fair assigning you a bunch of these. Questions on the procedure here? A fun game to play would be to try and find your interval of convergence for this power series. Now, the 2 to the n and the n factorial really do want to help this thing converge, but this product upstairs is hurting it. So we might have a finite IOC, and that'll be an interesting thing to see if you can find. Of course, other fun stuff would be trying to integrate this function by integrating these. The integral of this function is not hard, so it's not something you would need a power series to do, but good practice. Okay. We have about 2 minutes left in class. There is one other fun kind of problem where you infer information about derivatives of a function using a known power series. I think we'll save that for next time because I do not want to give you too much in one sitting, and I feel like this is fairly intense. So I'll go ahead and end it here. I know that Fabrice, you said you want to talk, so we can hang out to chat for a second. Otherwise, I will see you guys on Friday. And on Friday, we're going to introduce the last bit of material for this class. So the last few things we do here is look at parametric equations, so curves defined by parametric equations, which are quite cool. In that context, we'll study arc length and surface areas. We'll also talk about like tangent lines, all the basic calculus stuff. And then finally, we're going to do some work in polar coordinates, which is another sort of way of describing curves in 2D space. So this is the end of our study of power series, except for that fun little derivative problem that I'm going to push to Friday. And after that, we'll be moving into chapter 10, where we're kind of taking a step back. So we've made it through the toughest bit of material in the course. Please invest your time wisely, solving homework problems, solving problems from the textbook, making sure you're really comfortable with the notation and these procedures. I know that some of these can feel intimidating. So don't hesitate to come by office hours or ask for help. I really want to be there for you. If there's something you're struggling with, please ask for help. But that is it from me. And I'll see you guys next time. All right. And then Fabrice, there's a few people hanging out. So let me just go ahead and make a breakout room. I'll send you an invite and then follow you in. All right. How's it going?
Pretty good. Not bad.
Cool. Okay. What did you want to talk about?
I just wanted to know how am I doing like overall in this class.
Let's take a peek. So Not bad, not bad. The exam 1 score looks like was a 61, and the exam 2 score was a little lower at 51.5. Neither of those are like unsalvageable. The 51 is not ideal. Exam 3 is going to be important for us. The final is definitely going to be important for us. Right now, what I'm showing is your overall average in the class is a 61.11%. I can add in the homework score kind of as it is so far and see what that does for us. How has the homework been lately?
It's been pretty shit, but it's like it takes me a long time.
That's okay. Yeah, it's tough stuff. It takes a while, but as long as you're getting through it, that's good. So
yeah, I just find most of the time myself like improvising and stuff when I'm doing stuff, but it's like I don't
know. If you find yourself feeling lost on the homework, don't be shy about bringing those problems to office hours. I'm happy to work on them with you there. And that can be a big help, can save a lot of time. So it looks like we've got 553 out of 595 minus 39. So that's 565, 556. Oh yeah, man, you've got like a perfect score in the homework. So if I add in your homework average as it is right now, we're going to have 45 there. Close this and we calculate. It's not showing as a line on. That should bring you up a little bit. Scrunch these down a little. We haven't done yet. So, yeah, with the homework in, I'm showing you at 67.59. So if you're able to keep the homework going as it is, right, keeping up with the homework, making sure you're finishing all that stuff, and the exam average doesn't drop, then I think you'll be in good shape here. So what we need is for exam 3 and the final to be somewhere around 70. If exam 3 is like another 60-ish thing, and then you were to get a 60 or 70 on the final, let me see what we would be at there. So let's say exam 3 is like a 55, and then the final exam is so 105 out of 150. That means we will replace this by 70. Yeah, so if exam 3 is like a 55, kind of between where your last two exams were, and then the final exam is a 70, that would bring your grade to a 69.42%, which is right at that threshold where I would round it up to a C. So it's definitely still possible to earn a passing grade in the class. I think the most helpful thing you can do, because the final exam is generally a little tricky, right? There's like stuff from the whole semester in there. The best thing we could do to like guarantee that you're going to get through the class with a C or better would be to try and earn as strong a grade as possible on exam 3. So I would say study this power series stuff. In the next few weeks, really just pour time into this stuff and make sure that that goes well on the test. And then I think you'll be fairly safe coming into the final. You know, if we could secure something strong on exam 3, like 75, that would be enough to bring you into the C range, and then we just need the final to not bring us back out.
Yeah.
If you were to get like an 80 on exam 3, that would bring you up to like a 71. And then on the final, we would just need to maintain. We wouldn't need to worry about trying to claw our way up from there.
All right.
How are you feeling?
It's like I know I want to like my major is computer science, but I'm also in the process of thinking about changing everything.
Computer science is a cool degree. There's a lot of fun stuff in there. What is it about computer science that interests you?
Well, I wanted to learn it just for personal use. So when I have my own business, I can set up my own software, stuff like that.
I see. I see.
Yeah, that's the main reason why I wanted it. But it's like I lost interest in it. So
Is there a certain kind of business that you're hoping to run?
yes,
What
I'm
is
more
your
like I love fashion, so I design clothes.
Oh, that's cool.
Yeah. So it's like I wanted to have my own software when I have my own store, stuff like that. But I'm more focused. I'm also more focused on my fashion career. So it's like it's really tough right now.
Yeah, that's an interesting blend of stuff. So like wanting to do computer science to further a career in fashion design. There might be some neat ways to kind of mix those things together. I know UF has some, what do they call it? Interdisciplinary programs where you can kind of take part of one major and mix it together with part of another major. And that might be something to look into. It might kind of require a little bit less of the mathematics than a pure computer science degree would, and let you focus a little more on the fashion, while still getting to do the parts of computer science that you would want for your business down the line. That's not something that I know a lot about. Like, I'm not sure what sort of fashion-oriented stuff UF has, but it might be worth something to look into.
Yeah.
But yeah, that's neat. And I think right now you're in a reasonable place with this class. I wouldn't panic, right? I think you can definitely get you through this. We just want to make sure that we do as strong as possible on exam 3. That's going to be the main thing. All right.
Yeah.
Is there anything else I can help you with?
No, that's all. I just wanted to know how I'm doing overall.
All right. Yeah, right now you're not in terrible shape. We're at a 61. We want to bring that up with exam 3, and then you'll be in a nice safe spot.
All right.
All right, buddy. I'll see you later.
All right. Have a good day.
Take care.